Thank you. So today I'm going to talk about how you cluster curves or how you cluster trajectories. So yesterday we focused only on how you actually compute the distance between two curves. So today I'm going to try to use that to see if we can cluster curves. Okay. So, if we have points, we all know that what a cluster is, right? Or what clustering is. A cluster is a set of points. Usually you have some kind of bound maybe on the number of points you want to have in a cluster. So maybe you say, I want to have at least m points inside in the cluster. And I want the distance between the points in this cluster to be small. That's usually how we define a cluster. Okay. So what do we want with when we want to cluster curves? Well, so again, we want to group similar subcurves into a cluster. Right? It doesn't even have to. Okay, so I'm talking about subcurves, but let's just consider curves for now. Okay, so you want the distance between the curves in a cluster to be small. Okay, and you probably you want a minimum number. So again, maybe you want m curves, and you want all these curves to be close to each other. And again, we're going to use the Frechet distance. So do we need any additional constraints on the clusters? Or do we need any additional constraints on the curves in the cluster? Oops. Okay, so just to see, what I'm going to do is actually I'm going to look at subcurves or sub-trajectories of one single trajectory. So as input, I'm giving one long trajectory. And I want to find sub-trajectories or subcurves of that trajectory that are similar. Okay? So in this case, for example, I would say that these three sub-trajectories are fairly similar. So that would be one cluster of size 3 and some distance. Okay? And this we use this quite a lot for different applications. I mean, it's such a fundamental tool to use clustering. So here, this is tracking seagulls. And there, again, you want to find what are the most common trips they do, for example. So here, it turns out that the seagulls, this is where they live. And then almost every day they perform a trip down to this area. This is actually part of the Netherlands. They perform a trip down to this area, and then they go back. They spend about a couple of hours there, and then they go back. And if you look at Google Maps, it turns out this is a garbage dump. So the seagulls go there, they feed from the dump, and then they go back. Here's another example, a football example. So this is Fabregas, when he was playing in Arsenal. And here you want to look at his most common movements, right? So he has a lot of, maybe many of you know that he's a midfielder. So he does a lot of movements, a central midfield. So he does a lot of movements from along the central midfield part. There's a better photo of it, maybe, a picture of it. Here's another example where we have Nasri when he was playing in Arsenal. He plays in the left side, and he performs a lot of runs into the central part of the penalty area. Okay. So, as I said, we're going to use the Frechet distance. And just to recall what the Frechet distance is. So, it measures the similarity between two curves. So, we have two curves, the blue one and the red one. And the easiest way to think about it is to just set a person walking along the blue path and a dog walking along the red path. And then we have to move the person and the dog from the start of the curves to the end of the curves. And we want to minimize the maximum distance between the person and the dog. So we're allowed to control the speeds, but we're not allowed to go backwards. So the Frechet distance of the two curves is the minimal leash length necessary for both of them to walk from the start of the curves to the end of the curves. Okay? So I hope you'll remember this from yesterday, at least. And this is the more formal definition that says that you have two polygonal curves, P and Q. And the Frechet distance is where you take all the reparameterizations, alpha and beta, going from the start to the end. And you want to minimize the maximum of this distance. Okay? And of course, then you have to start at the start point, and you have to end at the end point. Okay? Good. And yesterday I showed that there is a decision algorithm that says, is the Frechet distance between the two curves at most some r? And what we did then, we computed for each segment of the polygonal path. So each pair of segments will generate a cell. Then each cell we compute what we call a free space, the white space. And then we get this free space diagram that has a part of white space and a part of gray space. And if there exists a non-decrease in xy monotone path, non-decrease in xy path from the bottom left point to the rightmost point, then we know that the Frechet distance between the two curves is at most r. Okay? So building this free space takes the complexity of Q times the complexity of P, because we have to look at every pair of segments. So if we have M in one and N in the other, the construction time for this is M times N. Then we build a network on what we call the critical points. And that network will have complexity M times N. And then we just decide if there is a path from the bottom left point to the top right point by breadth first search. So that will again take M times N. So the total time to decide if the Frechet distance between P and Q is at most r will cost M times N. Okay? So let's go back to the clusters. So I just want to add a couple of fairly simple constraints to make it maybe a bit more clear what we want. So I have a polygonal curve T. I have an integer M, and I have a distance D. So I want to find, so a cluster is M subcurves of T with distance at most D between any two subcurves. Okay? So that's very much like the standard definition of a cluster for points. But are there anything we have to be a little bit careful of? So one thing that is generally required in the literature is that the subcurves do not overlap. Right? So say I want to find I want to decide if this trajectory, this curve, has two subcurves that form a cluster. Right? So maybe this would be the first subcurve, and this one has a small distance to this subcurve. Right? So the distance between these two is maybe very small r, but they overlap. Right? Which doesn't really make sense for most applications. So usually you assume that the subcurves are disjoint. Okay? So these subcurves have to be disjoint. Okay, the second thing that we usually require is that the length of the clusters are maximal. Right, for example here, if I say that the distance is D, and I say that the cluster size is 2, well then any pair of points here will form a cluster. Right? This point with this point with this point with this, so we get an infinite number of clusters, right? So usually what we assume is that I have a maximal length of the cluster. Right? So in this case, for example, I would have a cluster that might go all the way over here. Right? So I don't want to report every possible cluster, because then I would just get an infinite number of clusters. Okay? Okay, so I'm given a curve T, a subcurve cluster, which I will denote by SC. So it has three parameters. M is the number of subcurves. L is going to be the length of that subcluster. And D is the distance between any pair of subcurves in my cluster. So it consists of M subcurves such that the subcurves are pairwise disjoint. And the distance between any two subcurves is at most D. And at least one subcurve has a length at least L. So it's more or less a decision problem, right? I just want to see, is there a subcurve cluster with these three parameters? Okay. So here is if we want to look at it from as a trajectory, you have one trajectory, and here the path will form a cluster of length of size 2, and we want to have it as long as possible, so it will be this. Okay. And the distance between these two sub-trajectories should be at most D. Okay. Okay, and the subcurve clusters is assumed to be maximal. So we will report the whole cluster. Okay. And now, before I was talking about curves, but of course we can do exactly the same thing for trajectories. Okay, good. Yeah?
This distance that you are talking about is a distance that is determined with Frechet distance?
This is the Frechet distance.
I think this is important, that how much these two curves are far away from each other.
Yeah.
Not how much they are similar. You are talking about Frechet distance talks about similarity, but here we talks about how much they are far away. If two curves are similar but they are far away from each other, you do not cluster these two with them.
Yes, you're right. So it's the Frechet. When I say similar here, I meant the Frechet distance. But you're right, it's not really a correct use of the word similar. So it's the Frechet distance that should be small.
And how much they are far away. I mean, if two curves are similar, but they are far away from each other, you do not cluster these two in one cluster.
Yeah, but if they're far away from each other, also the Frechet distance will be big. So the Frechet distance will give you, hopefully, that they are similar and close to each other. Yeah, that's clear? Yes. Yeah. Good. Okay, so this decision version is there a subtrajectory cluster of T that contains at least M subcurves? The length of the longest subcurve has to be at least L, and the distance between every pair of clusters is every pair of curves is at most D. Okay. And then, of course, there's an optimization version also. And the optimization version I will look at is to make the clusters as long as possible. Okay, but you could also look at optimization's version where we maximize M or D, but I'm going to look at the length.
So you maximize the length of the longest in the cluster?
Yes, the length of a cluster is the length of the longest subcurve in that cluster. That's also, I mean, it's not, there are different measurements here, but I think this is maybe the most reasonable one.
We do clustering in just one curve, yes?
Yes, exactly. So we have one long curve and you want to pick out pieces of that that have small Frechet distance.
Yeah. Why don't we say the order of the sub-trajectories? For example, when the curve is something like a zero, the number of the order of each sub-trajectory is that all contain just one cluster. It would be a great option for a person to have the order of each sub-trajectories in a class, in a cluster.
You want the sub-trajectories in a cluster to be ordered?
No. the order in the spiral form,
Yeah.
the curve itself, the order of each subtrajectories in this shape, in the spiral.
You mean the order along the trajectory?
Should be preserved in the cluster, I think. How can we have this order preserving property for each cluster? I think it would be if we separate each cluster and then we're going to combine them. How can we manage the?
Yeah, I don't know. Why do you want to preserve the order?
Why do we cluster the trajectory?
But the order, you mean an internal order, or?
Internal order of each cluster.
So, for example, if you look at it, a cluster for points, what would the order be there?
What points? I'm thinking about something like puzzle. For example, we have some lines in a puzzle, and when we are going to match each of them, we have some order between any lines.
Okay. Okay. I never thought about that problem, but that might be a nice problem to add as such a constraint. But I never thought about it actually. Yeah. And maybe even the algorithm can actually be to handle this case. Yeah.
You don't accept any trade-off between these three parameters?
So at the moment I'll just look at the decision version. But you're right. So when we apply it, we usually let the user set the three parameters, and then he can just play around with. So if he wants many clusters, maybe he sets small ML and D, or ML and then a large D. But then you can just play around with it and see. So you can try to get long clusters with few members, or many members, but maybe shorter. Okay, so unfortunately this is a fairly hard problem. So first of all, if we want to find any approximation of where we want to maximize the length of a cluster, this is three-sum hard. So that implies that it's unlikely that we can do it in subquadratic time. Okay, this is not a huge problem, of course. But the other thing is that this decision problem is NP hard, NP complete, right? And we'll also show that even if we want to have a 2 minus epsilon distance approximation, so you want to, so the distance, the Fréchet distance d, even if I would allow a larger distance, it is still very hard to approximate it, right? So I'll show you later on what this actually means. So I'm going to show you that this decision problem is NP complete. Okay, and I will do a reduction for max click. So the decision version for max click is there a click of size k in a given graph G? Okay, so the max click, so the k click is other k vertices that form a complete subgraph in my given graph. Okay, so for example, if this is my graph, then this subgraph forms a click of size 4, right? Because it's a complete subgraph of those 4 vertices. And it's known that this problem is very hard. So I'm going to show you how we can solve this decision problem by computing a subtrajectory cluster of a trajectory. Okay. So just for simplicity, I'm going to make. I'm not going to look at one big trajectory, but you can put them together. So I'm going to create 1, 2, 3, 4, 5 subtrajectories. Okay. So this is, let's say that this is our graph. This is our input to max click or k click. Okay, so now I go through all the vertices in the graph. So let's start with A. So I put A at the top here. Then I put a point for all the vertices in my graph that is connected to A at a unit distance vertically below. And all the points that are not directly connected to A by an edge in the graph, I put at a distance 2 vertically below A. Right? So this is a distance 1, this is a distance 1, so the distance is 2. So let's assume that I want a Frechet distance of 1. So I should maybe be more clear. So this is distance D, this is distance D. Okay. And then I do this for every vertex in the graph. Right? So here I put B. B is connected to A, C, and E. So I put A, C, and E at the distance D below. D is not connected to B, so I put that as a distance 2D. Yeah? And then I just continue like this. And let's assume that this distance is fairly big. It's just that I can't fit it on the screen, right? And here again, C is connected to A and B, so I have a distance D. D and E is not connected to C, so I have a distance D. Okay? And now I build a subtrajectory of each of the vertices. So for A, I will get the following subtrajectory. It starts at A, then it goes through all the points that are marked A. So it's a purely X monotone path. Okay? And then I do the same for all the others. I get B. So B starts here, then it goes up to where it's selected, and it goes down and follows all the B. And you do the same for C, the same for D, and the same for E. So now I'm saying, find me a cluster, a subtrajectory cluster of at least size M, and that covers all the whole sequence. Right? So it has to start here and it has to end here. Okay? And I know now that the distance between these are exactly D. So let's look at a cluster. Right? So I'm just going to approximate the Frechet distance with a disk in this case. So since this is exactly D, I can fit A and B, C, D into this box, into this circle, right? And I can, if I want to have B, C, and D in here, I can choose to either have A or E. I cannot take both of them. So I have to make a choice when I create my cluster. Either I include E or I include A. I cannot include both of them, right? So I have to make a choice, either A or E. And now I start to move this. And what happens here is, here I chose A, here I chose B, here I chose C. And then, if I want to keep A and B and C in my cluster, I have to go down and pick up this one. Right? Then I can get A, E, and B, C. E I already missed. And here I get B, D, and AC. Right? So I get the following cluster. Okay, so it's clear here that I will lose out on E and D, D and E. Right? So it turns out that A, B, and C, they form a clique of size 3. And it's easy to see that if I require, if I set the subtrajectory cluster to be of size M, then I will get a clique of size M. So if there exists a subtrajectory cluster that contains M trajectories, then I will get a clique of size M. Okay. Is that clear? Okay, so the problem is as hard as max clique. If I can solve this problem, I can also solve max clique. So since K clique is NP hard, I know that the decision version of our problem is also NP hard. So there's a nice little observation here that here I'm saying, okay, this might have size D, right? And this means that I have to choose either A or E. But I can actually make this ball much bigger, right? I can actually make it almost twice as big. And since I can make it almost twice as big and still get the same result, I know that even if I allow a 2 minus epsilon approximation for the distance, I will still get exactly the same result. Right? So if I can find, if I can decide if there is such a cluster, even if I allow a bigger distance, so even if I allow almost twice the distance, then I can still show that the result I get is equivalent to a k-click for the click problem. Okay, and for the case where you want to maximize the number of members in the cluster, then you can even show a slightly harder proof. So the problem of computing a 2 minus epsilon distance approximation of where you want to maximize the number of subcurves is at least as hard as approximating max click. And I'm sure most of you know that approximating max click is a very, very hard problem. Okay, good. So the question now is, can we find, so say we know that we cannot really do anything if we allow 2 minus epsilon. But say we allow a 2 distance approximation. Can we then get a reasonable algorithm for it? So let's study the Fréchet distance a little bit more before we start discussing the algorithm. So we get a set of polygonal curves. So the Fréchet distance of f can be computed by computing the Fréchet distance between every pair of curves, of course. Right? So I get a set of them, and then I compute every pairwise distance, and the maximum of that will be the distance, the Fréchet distance in that cluster. So I just take all the pairs of subcurves, and I compute the Fréchet distance. Okay, so that you can do in ni times nj log nij, and you have to do this for every pair. So if fi is some n divided by m, then we get some running time like this. So this is not really a good solution. So is there anything we can do? Well, the nice thing with the Fréchet distance is that it's a metric, right? So Dumitrescu and Rothe, they showed that if the distance between the curves f1 and f3, so they show that the distance between f1 and f3 is smaller than the distance between f1 and f2, and the distance between plus the distance between f2 and f3, right? So that's fairly easy to see. If this is f1, f2, and f3, you can look at the parameterization. Now this point has to be mapped to a point on f1. This point has to be mapped to a point on f3. We know that this distance, say that this distance is A, this distance is B. Well, then the distance between these 2 points will be at most the distance B plus C. No, that's not really true, is it? No, the distance is, of course, at most A plus B. Okay? I'm just testing if you're awake. Okay. So can we use this observation to get an approximation? Well, so we have the same setting again. We have a set of m polygonal curves. But now I'm going to select a representative curve, f1 of f. So I just pick f1. And then I compute the maximum Fréchet distance d between f1 and all other curves in f. Right? Well, since it's a metric, I know that the distance, the Fréchet distance of that cluster is greater than d, greater than or equal to d. But it's at most 2d because of the triangle inequality. Right? So between every pair of curves, the maximum Fauché distance is at most 2D. So this gives a 2-distance approximation. So how can we use this? Okay, and the running time is of course much faster, because now you don't have to sum over all ij's. You only have to sum over n1 and ni.
So which version of the problem are you? The max length?
Yeah, I'm still going to do the max length, but now I'm going to allow a 2 approximation on the Fauché distance, because I know I can't really do anything if I allow exactly the distance d. So I'm going to relax the setting and say, instead of allowing exactly distance d, I'm going to allow a distance 2d. Okay.
So that's like exact distance.
So the user will give me d, the distance d, and I'll say I can't do it, but I'll give you something with 2d instead, at most 2d, because that's the only bound I can prove. Yeah.
What about the sum of errors?
Sum of
Errors, sum of distance. Here you check the maximum, right?
yeah.
But in some problems, maybe the sum of distances.
If you want the sum of distances,
You change the metric.
I don't know. Sum of distances. I don't know how you would do it, actually. I mean, I think you have to change, because it changes the problem very much, right? It becomes very different. Yes, yeah, I'm sure it will be much harder. Yeah, I don't know. It's a good question. No? Okay, so just remember the decision algorithm for just a Fauché distance. Right, so we just want to find, we build a free space diagram, and then we want to find if there is an xy monotone path in the white space. Then the distance is at most r. Okay, so let's state the problem again. So we want, given a trajectory T, a subtrajectory cluster with parameters m, l, and d is at least m subtrajectories. They're pairwise disjoint. The distance between any two is at most d, and at least one of the subtrajectories has length l. Okay, and now what I'm going to look at, I'm going to try to find the longest subtrajectory, the longest subtrajectory cluster. And I'm going to approximate, right? So I'm going to allow a 2d instead of d. And for this presentation, I will just assume for simplicity that all the subtrajectories will start at a vertex and end at a vertex. Okay. The algorithm I'm presenting can actually be modified for not including this constraint, but the presentation will be much easier if I assume it. Okay, so I'm going to use the free space diagram. But before we computed a free space diagram between two paths, P and Q. But now I'm going to create a free space diagram between T and itself. Okay? So it will look something like this. Is not a very good example, but it's very hard to make good examples for free space diagrams. So just maybe it's interesting to see that the diagonal is always white. Why is the diagonal always white?
What truth the dog and the person have the same speed in the same point to be
yeah, because they walk on the same path, right? So if you set them to walk together, which they do if they walk on the diagonal, then the distance between them will always be 0. So the diagonal is always white.
Sorry?
Huh?
According to the diagonal of this free space diagram, this is symmetric. Why this property holds in this case?
Why the property holds?
The symmetry is symmetry according to the diagonal of this shape.
Yeah?
can you explain that the diagram is symmetric?
Oh, why it's symmetric? Yes. Well, so say I take a point here. Okay, that corresponds to this point here and this point here. Right? But that's on the same curve. Right? Because this curve is the same as this curve. So this point here, it also exists here somewhere. And this curve here also exists there somewhere. Right? So that's where you get exactly the same. That's why you get the symmetry.
Exchange the man and the dog.
Yes, you could also say that. Just exchange the man of the dog. But sometimes you don't have a man and a dog, you know. Okay, so as you see here, the white space is very small. And it seems that it's very hard to find a path here if you don't go along the diagonal. But let's say that we grow R a little bit. So we just want to, so we grow the distance a little bit, right? So we're saying what if we allow a bigger Frechet distance, what can we do? So then I just want to show you the following observation. Say I look at an XY monotone path in this white space. Okay? So what do I know here? Is there anything I know that I could maybe use? So this XY monotone path, it will correspond to a subpath on T, right? Down here. So this is a subpath of my trajectory. But then if I look at the vertical projection, that will also correspond to a subcurve on my trajectory, right? And what is the distance between these two subcurves? Smaller than R, right? Because I know that there exists an XY monotone path from the bottom left to the top right of this. So I know that the Frechet distance between this and this is at most R. Okay? But then it seems that maybe there are other XY monotone subcurves for this one, right? So here, for example, we have another one, right? And this, again, corresponds to a subcurve. So now we know that the distance between this and this is at most R. Distance between this and this is at most R. Okay? And here, of course, we also get the diagonal, right? So that's just saying that the distance between this and itself is at most R. Well, it's 0, so we Okay, so let's say that we have these three subcurves. We have what I will call the representative curve, is C. So the curve on the horizontal axis will be called the representative curve. And then I have the two subcurves A and B. And I know again that the distance between them is at most R. So what do I know about the distance between A and B? Yeah, what is the Frechet distance between A and B? Smaller than 2R, right? Because I know the Frechet distance between B and C is at most R. And I know the Frechet distance between A and C is at most R. So since it's a metric, I know the distance, the Frechet distance between A and B is at most 2D. Okay? Good.
All these sub-trajectories belong to just one class, class 3S?
Well, this is, well, you could say that, yes. I mean, if our cluster should have three subcurves, right? And if the Frechet distance is at most D, and this is long enough, then it's a cluster. Okay? So again, I want to call C my representative curve. So C is the one that the length of which I will measure. Okay? And I say, as I said before, the length of a cluster is the length of the representative trajectory. Good. So now look at another example. So I don't know if you can see this, but here I have a curve or trajectory. And as you can see, there's 3 subcurves that are very similar in this example. So the free space diagram of that is this. So it's a free space diagram by the curve and itself. So again, the diagonal is white. Okay, and I want to find this cluster. So what does this correspond to in my free space diagram? Well, it corresponds to some subcurve on the horizontal axis. And then some subcurves on my vertical axis, such that for each pair of them, I will find an xy monotone path. Okay, so it could be, say, my representative curve is this. Okay. Well, and there is another one. Right? I have 2 of them, and actually I will have 3 of them. Okay. And for each one of these, I can find 3 xy monotone paths. Right? So that will mean that I have a cluster of size 3. The Fauché distance between any of these 3 curves is at most 2d. And the length, well, that depends on the length of this subcurve. Okay. So the algorithm is fairly simple. We're going to sweep the free space diagram from left to right using 2 vertical lines. And what we want to do is try to, between the 2 lines, decide if there are m xy monotone paths in the free space. Okay. So we sweep, and then at each event point decide if there are m monotone curves between L and R. And while we sweep, we maintain a network of the critical points. So it's exactly what we did yesterday on the free space diagram. Yesterday at the free space diagram, we computed a free space and then computed a network of that. But here, we are going to do it step by step. So every time you add a new one, you will add the critical points for those cells. You can actually pre-compute everything, but then you will lose a little bit of space, and I'll come back to that. But you can assume that the whole network is given, the whole network of the critical points. Okay. So I'll sweep L and R. So at each event point, I decide if there are m monotone curves between L and R. Okay. So if I answer yes, well, then I want to make it longer, right? Because I want to report the longest cluster. So that means that I will move R 1 step to the right. Right? And then again, I'll just check, do I have m xy monotone paths? Okay. If I don't have m xy monotone paths, and the distance between R and L is 1, then I move R 1 step to the right. But actually what I will do is I will move both of them 1 step to the right, because I'll move it right, and then of course in the next event I won't have M again, so I will go to this. If no, and the distance between R and L is greater than 1, then move L to the right. So I will just more or less move L and R to the right until I find M monotone paths between L and R. So let's see. So for example, I start here. I don't have M monotone paths, so I move, and R minus L is greater than 1, so I move L to the right. Again, I don't have M monotone paths, so I move R, and I move L, and I continue like this until I find M. So let's say M is 3. So here, all of a sudden I found M monotone paths. Okay? So I have M monotone paths, and then I start to grow. I start to make the cluster as big as I can. Right? Keeping the left side fixed. So I will grow it. Again, I find M monotone path. I grow it, and I grow it, and I grow it, and I grow it as long as I can. At some point, there are not M monotone paths anymore. Okay? Then I move the left side, and I start moving again. Does this make sense? Is it understandable? Yes?
There is always an M monotone path in the diagram.
No, it's 1, but M could be big, right? M, in this case, for example, I set M to be 3. But you're right, I will always have 1. Always have 1. Yeah. So do I talk too fast, or I expected this to take at least 2 hours.
So do you also have to check that, or you don't do it at this point, that these paths are still disjoint?
Yeah, I'll come to that. So now I just decide if there are M monotone paths. But how do I decide if there are M monotone paths? I mean, this is so now I just use it as a black box. I'll say, are there M monotone paths or not? Okay. But of course I have to compute these paths. How do I actually compute them? Yes?
Each path corresponds to two subcurves of a curve.
Yes.
So what if these subcurves have non-empty union?
Yes, I'll come to that. Yeah. Yes.
So when you move the right segment and you don't find the XY monotone path, then you move the left one, right? So what if there is a XY monotone path before this? So I mean it starts before R, before the new point that you selected as left point, and have a different.
So what do you say? You say you have L, and you have R, and here we do not have. So here we have less than M paths, and now you're saying now I move L.
So, for example, in the figure in the slides,
Yeah.
maybe there is another XY monotone path that starts in the middle of this area, this white area.
Yes. I move this. Yes, you're right. So actually, I just move this step by step, right? So I will move L here, then I compute it again, and then I try to move R. I can't move R. Then I move this one to the next one. I try to move R, and maybe I can move R now. Yeah. So you're right. I have to check all of them. Mark, you seem.
No. So when you write M monotone curve between L and R, you mean going completely from L to R?
Yes. Maybe it should be more clear. You should start at L and end at R. Yep.
How to determine that maybe we found the algorithm found two paths that are in one area.
Yes.
How we
So I'll come to that because I haven't discussed how I actually find this path. Right. Now I just say I have M paths, and then I'm happy. Right. But I haven't discussed how do I actually compute these paths. Yeah.
Sorry. We manage the sweeping line in this axis search for the passes. I'm thinking about how we change the axis to the y-axis and do the search again in the y-axis. I think when we have some sub-trajectories in just one class in rectangles that's parallel to the y-axis, we can have some passes that have the same property and they consist in one cluster that lays on the of the trajectory in the y-axis.
I don't think so because no, this is completely symmetric, right? So this one, if I sweep from along the y-axis, then this will correspond to this. Right? And then I get exactly the 3 subcurves. Because this one will correspond to this. This one will correspond to this. This one will correspond to this. So I get the exact same result if I sweep from along the x-axis as I would get if I sweep along the y-axis.
How about mid-class matrix? For example, anything that has problems being symmetric, because I think we have an intersection between these 2 parts, 2 triangles that intersect in it.
Yeah. So say I would have look at 2 trajectories, right? I mean, to run this algorithm, what I could do, I could just connect them by some point very far away, right? And now I could run the same algorithm. Yeah. Yep. It's good that you ask questions because questions takes time. So. Okay, so the first thing, what is the number of event points we have? How many times do I have to ask the question, are there m monotone paths?
An area starts and ends.
Yeah, and how many times is that? Huh? Now, just how many times do I have to move L or R?
Twice the number of nodes.
Exactly, right? Because I moved this monotonically. So I'll move R along here, and of course I will stop at most n times, right? And then I will move my left, and that will again only stop n times. So the total number of events is only 2n. Okay? You look like you have more questions. No. Okay. And then, yeah. Okay.
So, if you want the question, the simulation you just showed is not the way it moves, right?
No, that's true, because I will actually move step by step.
Plus, you're moving R. I mean, you're already starting to move R. I think in it where you already.
Yes. This is just so. Oops. So this animation is only there to make it look nice. Okay. Yes. So we have 2 types of events. L moves to the right and R moves to the right, and they do this step by step. So now the big question is, so we have 2 n events. Now the big question is, how do I handle an event? How do I decide if there is an XY monotone path? Or how do I decide if there are m XY monotone paths between these 2? Right? So I want to decide if there are m non-overlapping, right? So they have to be non-overlapping along the y-axis. Okay? Between L and R. So let's look at L and R and assume that I have my network. I have my network for the critical points. Okay, so I will start at the topmost corner of R. And then I find a XY monotone path from U to L. Okay? And I can do this in linear time with respect to the size of the network, right? I just do a search. But that's not enough. What I'm going to do, I'm going to find the topmost point on V that I can reach with a XY monotone path. And again, I can, because the size of the this network is maybe n square, and I can just search for the topmost point I can reach that they can reach on L. So maybe that's U prime, and that will be my first path. Okay. Okay. So now the observation is that no point on R below U can reach a point on L above U prime with a XY monotone path. Why is this true? Oops. Well, you saw it, right? Yeah. So if there is a point below you that can below you, so let's call it V, and this point can reach a point V prime that is above, well, that means that the two paths, they have to intersect somewhere, right? Now I have an XY monotone path to this point, and then I have an XY monotone path to V prime, so I will have an XY monotone path between U and V prime. But U prime was the highest point that it can reach. So V prime cannot exist, right? So that gives me an algorithm, right? I start with the topmost point. I find the topmost point on L that I can reach with the XY monotone path. And then I jump down to the first point on R that lies below U prime, right? Because I cannot start above it. Why can I not start above it? Sorry? Well, there could be a point here, right? This point could be here, and it could find a path down here. But why am I not interested in anything that starts up here? Sorry?
Because we want to find the maximum length.
Yes, but I don't think this affects by this. Why? So I have L here, I have R here. I find, let's start. Okay, so this is U. I find the topmost vertex on L. So now why don't I just look for a next monotone path here? Well, so remember that this corresponds to a subtrajectory, a subcurve, right? And the distance between, the Fauché distance between the subcurve C, between L and R, has distance at most D to the subcurve A. Now, if I then would take an XY monotone path here, then I will get a new, right, B. But what is it? Yes, A and B overlaps, right? They overlap along the curve, and that's not allowed. They have to be disjoint, right? So the next curve has to start below this point, or below or on this point. Okay. So I find the topmost corner on L that can be reached by a XY monotone path, and I just continue until I either find M curves, because then I know I can say yes, or no more corners on R. So until I'm all the way down here. Okay? So if I come down all the way here, what do I know then? Well, then I know that there are not M curves. So then my answer is no. So either I find M curves and then my answer is yes, or I don't find M curves and my answer is no. Okay, so the only problem now is how much does it cost us to perform all these path queries? Okay. Okay. Well, so we know, let's do it this. So we know that computing the path will cost us time that is linear with respect to the size of the network. Okay? So let's say in worst case the size of the network here is n square. So that means that we more or less have everything in and everything. So we have a size of n square. So how many shortest path queries will we perform in worst case? N. Yes, n. We have to perform, because it could be that, we perform this query, we don't get anywhere. Then we have to go down one step, we perform a query, we don't get anywhere, and it could just continue like this. Right? We might never get to the other side. So we perform n path queries. And each query will cost, each query costs the size of the network. Right? So that could be n square. Okay? So that's only for one fixed LNR. So this is this is cubic with respect to one LNR. And then, of course, we have 2n events. So the total time is n to the 4. Okay? Good. So can we improve this a little bit? Okay, so there are a couple of things we can do. So one thing is that in most cases, this will not have width n, right? It will be much, much smaller. So if we set, so that means that the size, so before we said, well, the size of the network is n square, but if the length of this is, say, w, then actually what we get is order nw. I mean, in theory, that doesn't mean anything. That doesn't change anything, but in theory, it makes a big difference that you only maintain what is inside LNR. Okay, so that would mean that we get n cubed times w. The next thing is that, let's see. Okay, so this is just saying we get n squared per query, but if we set w to be the maximum distance between n and r and l, then we get n cubed times w. And the maximum amount of space we need to maintain is just the network inside this slab. So it's n times w. But maybe we can do even a little bit better by a very simple observation. So let's see if we can do this simple observation. So I have L, I have R. Now okay. So now let's say I find a path. Okay. Okay. And now I know, so how much time did this cost me? Well, actually, if I'm a little bit careful when I do the search, I never have to go below this horizontal line. Right? So I can restrict my search to this part. So let's say that this part is what do we call it? H1. Okay, and now I perform the next query, which will start here, and it will go down here, or maybe stop. I mean, I don't know. But then, when I do this query, I never have to go above this line, right? Because I have to be Y monotone. So I always have to go down. So I never have to look at anything here. Similarly, I never have to look at anything below this space. So that means that I have H2, and then I will continue like this. Maybe this doesn't work. But then I don't need to look at this. This is a little bit more tricky. But the idea is that I will never have to look in the same space more than once. Right? So I will never search more than the whole network. So the total search for all of these queries will be n times w. Okay. Yep.
Excuse me.
Yes.
Given a fixed L and R configuration, can't you use previous configurations to compute?
You're right. You can. The problem is that if you want to do that, you have to maintain a data structure. And that data structure is actually quite complicated, so I decided not to go through it in this lecture. But you're right. Because you all have already computed a lot of paths, right? And it seems silly not to yeah, exactly. So, and that's what we do in the paper. But this is a simple analysis. If you want to do that analysis, it becomes quite complicated, actually. Okay, so we can improve it to n squared w time and using n w space. Okay, so I only spoke about this case when the endpoints of the trajectory, so the curves, have to start and end at the vertex. But you can modify it with the same running time. But you only restrict the reference trajectory to be start and end at the vertex. And if you want to have no restrictions at all, you can do that too, but then you will start to lose quite a lot in the running time. And I'll show you this. Yeah?
If some way we found the middle of our space, the middle of our map.
The middle of our map.
Yes, because of the symmetry, it's not necessary that we check the other half.
No, it's remember that it's symmetric with respect to the diagonal.
Yes.
So not so that no, I can't do that because the symmetry is in the diagonal.
I mean, for example, the middle of L and R. Here is the middle of our map.
Oh, here?
Yes.
Yeah.
The line which is in middle of L and R is middle of our map. So
this one or?
No. The vertical line between L and R.
Yeah.
Here is middle of our map. The left of it is kind of is sort of similar to the right of it.
No, I don't think so. Because, for example, if I take this LNR, then you see it's very different from this part and this part.
Yes, it's true. But I mean, we can find a vertical line that is middle of our map. Here it is the line between this LNR.
Yeah, I'm not sure.
Look at the three space in the left that are similar to each other. Yes.
This one?
They are repeated in the right.
Yes.
You see this symmetry?
Yes.
Somewhere in our map that the left are in the right.
Yes. So it could be that you could save something, but even if you would do it, you would only save a factor of 2, right? But you're right. It might very well be that you could start to see, but the problem is that you will get different reference trajectories. This is a different reference trajectory from this, right? So now I was at least saying that that the length of the cluster is the length of the subtrajectory. The length of the cluster is the length of the reference trajectory. But however, you can change this. So there might be a way to save a factor of 2, but you wouldn't probably not be able to save more than a factor of 2. Okay, so what we do is we sweep in LNR and then we perform these queries. Okay? So the results we have is that if we want to use the discrete Fréchet distance, then we can do it roughly in n squared time. And that's quite very easy to implement, actually. So there are several implementations to do this. If we want to maximize the length of the cluster, and if we fix it to start and end at the vertex, then you can do it in this time, n squared w. And for most of the data we tested, w is very, very small, right? If you want to do it without any constraints on where the cluster can start and end, you have to pay much, much more. So then you will get up to roughly cubic. Okay. And this is actually quite tricky. It's a lot of details to get this to work. Okay, so we actually implemented so we use this, for example, in a football application, and the football application, the data sets for one play is about between 100 and 120,000 points. So doing the clustering took a very long time. So I had a student that was very good, it worked very well, and he actually implemented the GPU algorithm on this. And he did this on the continuous Fréchet distance. Right? So it's still very expensive. So 100,000 points takes about 500 seconds. However, since you use the continuous Fréchet distance, you can simplify the input path. Right? So I'm going to talk about how you simplify a path tomorrow, but maybe you've seen how you can do like Douglas-Poiker or something like this. So you more or less do shortcuts. You remove redundant points. And that usually takes down the data size to about 1/10 of the original size. And what you lose is very little in accuracy. And then, because we use the continuous Fréchet distance, we can use the simplification, which takes it to about 10,000 points. Then we run the GPU algorithm, and it takes no time at all more. Yeah?
How many cores did you have on your GPU system?
I have no clue.
The occupancy of the core?
Sorry?
What about the occupancy of the core?
I have to look it up. Because I didn't do any of the experiments myself. My student did it. So I have it on my computer, so I can. Okay. So there are a lot of very nice open problems here. The obvious question is, can we cluster faster? Right? And this is still very slow. Can we do this much, much faster? Can we even get a good approximation faster? So now we approximate the Fréchet distance, right? So we say, we allow the Fréchet distance to be twice of what is required. But could you do some other approximation? Or can we cluster faster for special cases? For example, if yesterday I was saying, if the paths are C-packed, then you can compute the distance, the Frechet distance faster. But can you cluster using this too? Can we cluster using other distance measures? So again, I think there was a very nice paper last year that proposed a new distance measure. It's not a metric, which will make it a bit harder. But it's a very nice distance measure, and it would be interesting to see if one could cluster using this distance measure. And the biggest problem of all, what should we report? Right? So I only said, let's find the longest one. But this is not usually what you want, right? Say I want to find, let's look at the football application, for example. I don't just want one cluster, right? I want to find all interesting clusters. But what does that mean? What does it mean to find all interesting clusters? Right? It's actually a very tricky question. And you can say, okay, I just report anything that fulfills the requirements. But then I will report more or less the same cluster many, many, many times. So if I have a cluster that contains, say, 20 curves, I will probably report that cluster 20 times. Right? Okay. Okay, so that's it for today. Any questions? Yes?
Actually, I have a question about this beginning part. So you have a curve, right, which is kind of directed.
Yes.
And you make a cluster. So it seems that in each cluster you cannot have two curves with different directions.
Yes, exactly. That's true. I cannot do. I can only do it with a directed curve.
Okay. So the direction is kind of
Needed.
here.
Yes. Yeah.
What is the characteristic of a situation that can help us to combine two clusters and just making this one cluster? We have the property that insists on the overlap. Overlap cause two clusters be in the same point. I simplified the issue. But what is the property that can help us to combine clusters and make a bigger cluster? We have the distance d for the longest curve and some other property for each cluster. But we have some small subclusters that can be joined with each other and make a bigger one.
So we don't use anything like that in our algorithm to join clusters, right? But
I'm thinking about when we cluster with respect to D.
Yeah.
When we change D, change to something bigger than D. How can we combine these clusters and make a new cluster fast?
Oh, that's a nice question. Yeah, that's a very nice question. I haven't thought about that. It would be interesting to see if you can say, okay, I already computed all the clusters for these.
Yeah.
Can I use them when I compute the new clusters?
Plus epsilon.
Yeah. I haven't thought about it, but that's a nice question. Yeah. Yeah. And of course also, so something that is also another very interesting problem is, say, I get the trajectories, or one trajectory, for example. I do a clustering, right? But then say, for a football application, for example, there is another game, right? So they're playing one more game. So the trajectory, in a sense, becomes longer. Can I use anything that I pre-computed to extend it? I don't know.
It is used in application, for example, trajectory, detecting objects, or even predicting the behavior of movement objects.
Yes. Yes. Okay.